All right, so let's take a look at the next couple of sections, 1.3 and 1.4, where we're looking at the limit of a function, and then also identifying, well, how do we actually calculate a limit of a function? All right, so it really makes sense to take a look at this function, x to the fourth. Where were we? Let's go back to what we had before. X to the fourth plus x cubed minus x squared minus x. Let's remind ourselves of our function. X to the fourth plus x cubed minus x squared minus x divided by x plus 1. All right, in terms of the limit of this function, right? Now notice we haven't graphed it yet. And so what we're going to do is we'll just go ahead and take the limit as x approaches some value, right? Let's say x approaches 1. Okay, we're just going to take the limit as x approaches some value. Let's say the limit LIM. So we're going to take the limit as x approaches some value. Let's say the limit LIM as x approaches 2 of our function. All over x plus 1. Okay, now what do we know about the value 2? I haven't sketched it yet, but I do know from our previous work that 2 is in the domain of the function. So what does that mean? It means I can use something called the direct substitution property, the DSP. We can use a DSP to identify what this limit is. And what does the direct substitution property entail? It says directly substitute into the function. In other words, the limit is the evaluation. This is very closely connected to a concept called continuity, which we'll discuss in a subsequent section. All right, so we got 2 to the fourth is 16, 2 cubed is 8, 2 to the second power is 4 minus 2, divided by 2 plus 1 is 3. All right, so we got 24, 20, 18 over 3. And I didn't even plan this, but we got a nice whole number, right, as our limit. So what's as our limit? So what's the moral of the story? The moral of the story is if I'm evaluating the limit of a function at some point within its domain, you down with DSP? Yeah, you know me. That's what we do. Just plug in the 2 and then you're through. All right, now, if we evaluate this limit, okay, now let's take a look at a different situation, right? So this is, let's say, number 1. Now number 2, situation number 2, we're dealing with a scenario. We want to find the limit, and the situation is a little bit more interesting. You're going to find out in the text that there's going to be a lot of situations where we find the limit of our function in a place where DSP is absolutely at a location where it's you down with DSP, no way, not me, is not going to work. All right. In a situation where you're down with DSP, no way, not me, it's simply not gonna work. And what location could that be in this context? Take a look at this rational function, and where would we be evaluating the limit in a location where DSP is not the way to be? Well, if we have -1, right, the one spot that's not in the domain of this function, if we have a -1 right there, then let's see what happens if we take this limit, right? If you try to use the DSP naively, so I'll put in quotations DSP, well, if I plug in a -1 in the numerator, I get -1 to the fourth. Do not forget your parentheses around the -1. Okay, -1 cubed minus -1 squared minus -1 divided by -1 plus 1. Now I'm looking at the denominator like, ooh, it's gonna be a problem. -1 to the 4th power is 1, right? -1 cubed is -1. Negative -1 squared is -1 plus 1. And we get plus 1. If I did my math right, that's looking like 0 over 0. Problem. That is a problem. It's looking like 0 over 0. Problem. We get 0 over 0. Problem. PROLLEM. That's a problem. All right. So what are we gonna do? What is 0 over 0? Maybe it's not a problem, right? Because I know if I have any number divided by itself, right? Let's go ahead and use the blue and use. Let's go ahead and use blue as our thinking color. Okay. So if I have anything divided by itself is equal to 1. So can I say 0 over 0 is equal to 1? Well, if I have 0 over any other number like 0 over 5, that's equal to 0. So is 0 over 0 like 5 over 5, or is it like 0 over 5? But then at the same time, I also know that 5 over 0 is equal to undefined, D and E. Let's say D and E right now, okay? So which one is this scenario like? Because it's all of these, but yet perhaps it's none of these. It's what we call an indeterminate form. And really what it's equal to depends on who wins. If I have 0 over 0, which 0 wins? Does 0 on top win? Does 0 on the bottom win? Or are they basically on equal footing? Right? And that's what dictates which one of these three scenarios effectively we fall into. So we're going to table a discussion of how to really, hammer these problems home until we get to L'Hopital's rule, right? But for now, let's take a different approach. If I'm taking the limit of a function, right, and the place where I want to evaluate the limit is in the domain DSP. If the place where I want to evaluate the limit is not in the domain, right, or more particularly, if I evaluate the limit using the DSP and I get an indeterminate form, like a 0 over 0, then I'm like, what the FERC? Yeah, what the FERC? Okay, FERC is going to be how we proceed. FERC. Based on the type of function that I'm dealing with, I'm going to do one of these 4 operations. If I have a rational function, which deals with polynomials, then we're going to factor. If I have expressions in a power, then we will expand. If I have root functions, then we will rationalize. And if we have fractional expressions, then we will combine. So what the FERC? In this case, we have a rational expression, right? This is a rational expression. And so we will factor. And so let's see if factoring gets us anywhere as we try to solve this problem. All right. All right, so let's factor. Okay, so we're looking at the limit as x approaches -1, x to the 4th plus x cubed minus x squared minus x all over x plus 1. How can we factor that? You may remember there's different ways to factor, right? If you have a binomial, a trinomial, in this case we have 4 terms, and so let's factor by grouping. We can identify the fact that we have, we can identify the fact that we have 2 terms here, x to the 4th plus x cubed. Then we have this minus x squared minus x. And let's see what we can do to factor these terms out. Okay, so we end up looking at the first 2 terms and having a common x cubed, x plus 1. I'll factor out the minus x, and we're left with an x plus 1 as well. Now these common x plus 1 terms are what are going to allow us to be able to factor by grouping. Okay, so we end up saying, well, it's almost like a reverse distributive property. We have the x cubed minus x on the left. Okay, so these x plus 1 terms that are common to both terms in the numerator is what's going to allow us to kind of use a reverse distributive property. Factor. All right, so we got that x plus 1 up there. In the denominator, we have an x plus 1 as well. Now, we knew that x plus 1 must be a factor of the numerator. Why? Why did we know that? Why did we know that the only way we could have proceeded with this problem is with x plus 1 being a factor in the numerator? How do we know that must have happened? We know that because when we plugged in a -1 to the numerator up here, we got a 0, right? And the only way that can happen for a polynomial is if it has a factor of x plus 1, okay? Right, and so the numerator has a factor of x plus 1, but guess what? So is the denominator. When we factor, we are exposed to the algebra we need to be able to proceed. All right, so here we go. We can factor out this x plus 1 in the numerator, bam. Denominator, bam. Why can I cancel them? Because if I can cancel those, technically I could cancel these, right? Well, the reason why we can cancel these down here and not up here has to do with what a limit is all about. What a limit is about is what happens near -1, not at -1. If we're at -1, then there's a 0 with 0. No way we can cancel those. If we're near -1, then these are not 0 and we can cancel them. Right, so that's a very important fact to remember about limits. Limits are all about what happens as you approach a point, but not necessarily at the point. All right, and so because we can cancel these, because they're not 0, they're close to 0 but not 0, we can cancel them. Then we have, so let's hit this with another thusly. Okay, the limit as x approaches -1 is equal to limit as x approaches -1 of just x cubed minus x. Now, let's go ahead and look at this algorithm and go right back to where we started. Where did we start? The first thing we started with was DSP, right? If I'm able to plug in a numerical value into a function, right? And if I'm able to plug in the numerical value into the function, and I get something that's, and I get something that works because that value is in the domain of the function, then that's what a DSP is all about. So now our function is x cubed minus x, right? And so we plug that in, and let's see what happens. -1 cubed minus -1. That's equal to -1 plus 1, which is 0, which is not undefined, which means the limit exists at -1. It just happens to be equal to the value of 0. All right, so in an interesting way, there's a sense in which the function we started with, this rational function over here, right, is somehow equal to equivalent to this function everywhere except at -1. Remember when we expressed it as a piecewise function up here, right? We introduced this 7 value. We kind of said, hey, it's acting one way over here and it's acting another way over here. Notice, because at this domain, we're able to factor this and cancel like we did in the limit. This function is equivalent to x cubed minus x here, right? And so that's something that's interesting about this function, that it can be expressed as essentially a polynomial at the locations within the domain. All right, let's proceed. The next thing we like to do is we like to use this Jupyter notebook to be able to find the limit of the function, right? That's our next thing. So where are we going to find the limit? We know that this function has a domain that's everywhere except -1. So we find the limit anywhere but -1. That's just a DSP, plug it in, evaluate, you're done, right? The one place where it's actually going to be interesting to identify what the limit is where we have a break in the domain, right? At -1. Now we already know using the DSP what's going to happen, right? Because x plus 1 is removed when you cancel the x plus 1. And so we're going to have a removable discontinuity, which means we'll end up with 0 over 0, but that 0 over 0 will probably end up being a real number when we evaluate. So how do we get AI to help us out with this task and show us the process as if we were doing it by hand? So what I want to do is I'm going to go ahead and paste this code. It says, show me step by step with no code how to find the limit as x approaches -1 of f of x. Use LaTeX so I can see it and mark down. Okay, so we go ahead and run that, hit enter, and here's what we get. Again, you see all the $signs and funny symbols. That means it's using LaTeX. So what we need to do, if you don't remember, is we need to copy that, paste it into a text box. And there we go. Okay, so, note that the AI is very particular. And you got to be very particular with your verbiage in terms of getting what you're looking for. You may ask the right question, but if you don't prompt the right way, right, then AI will not understand exactly what you need. Remember that this is a code block, and so the propensity is going to be to generate code. And sometimes we will need to use Python code to be able to get the answer that we're looking for. But right now, just at this beginning phase, we just want to see the generative capabilities of being able to see in mathematics what the answer is, right? So if we take a look at what we have right here, it factors the numerator up for us again, and then we write f of x in this way. We use DSP right after we do the cancellation. So that's what we got, DSP, evaluate the limit, and we get an answer of 0, just like we did in paper and pencil, stylus, and tablet.